Okay, in this video we're doing section 1-2. This is the sets of numbers, or the number sets that we're going to be working with. Now first of all, why do we need these sets of numbers? Because certain times in algebra or in any kind of mathematics there are certain rules or procedures that we have in place, but they're only meant to work on certain numbers. So we want to be able to put those numbers into collections that are easy to find and easy to follow. Okay, now the number sets that we're going to talk about are built in a very natural progression. How they're built when we start learning about math as a baby, through our lifespan. So let's start out. First number set, here are the natural numbers. Now I'm going to use this hashtag here just to be a shorthand for numbers. Okay, so we got natural numbers. The set of natural numbers is going to look like this. Okay, there's your natural numbers. Now we call them natural because that's how we naturally count. 1, 2, 3, 4, and so on. These three dots here are called the ellipses. That's just telling you that the pattern is going to continue indefinitely forever. Okay, these braces that we put on the side, that's just showing a set or a collection of something that we're working with. The next one, building off of that, is when we talk about whole numbers. Whole numbers are just going to expand on the natural numbers and start with that idea of 0. Okay, so we count. Well, what if there's nothing to count? That then includes that 0 idea. Now, one thing I want you to be very clear on is that this is not these sets are not disjoint. Okay, they build upon each other. So if you're a natural number, you're also a whole number. Okay, that would fit in that category. That's the same way as let's say you're a 094 student. Okay, you're also a JJC student. We're going to get a bigger collection of things. The next thing we talk about are integers. Okay, now integers give us another expansion, but it expands this way. What if there's nothing to count? Well, we get 0. Well, let's say our debt. Let's say we have a debt. That's going to bring in the negative numbers. So we're going to show that like so. Okay? So all natural numbers are also whole numbers. All whole numbers are also integers. Notice I just keep building. Okay? Now, the other thing I want to point out here, and this is just to kind of get you thinking a little bit outside the box. Okay? Natural numbers, there's an infinite number of them. They go on forever. Okay? However, we can still compare infinite sets. There's an infinite number of natural, infinite number of whole. But there's more whole numbers than natural numbers. There's more integers than whole numbers, and so on. Okay? The other thing that's really interesting is there's two types of infinite out there. There's countably infinite and uncountably infinite. Countably infinite doesn't mean that there's a certain amount of them, because infinite means it goes on forever. But these are countably infinite versus this being uncountably infinite. The difference here is I could say this is my first, second, third, fourth, and so on. I can't say that here. I can't say that there's a first integer because I could just keep going further and further to the left. Okay? Again, just something to get you thinking, get you kind of looking at things a little differently. So those are our first three sets of numbers. The next one is called rational numbers. Okay? Now, rational numbers are a little different because I can't really list those out. Okay? So I'm going to describe them instead. Rational numbers are numbers that can, I'm going to underline can, be written in the form, A over B. Okay. Now, A over B, there's your fraction, so they can be written as a fraction. Where A and B are integers and B is not equal to 0. Okay? Now, that not equal to 0 is very important. We never want to have a 0 in the denominator. Okay? Now, up until this point, we've just been building the entire time. First of all, we had our natural numbers. Just learn how to count. Then we kept those natural numbers through in 0. Kept the whole numbers through in negatives. Now, this does not exclude anything we've already talked about. The first thing was, it can be written as a fraction. Well, I can write all these as a fraction. All I have to do is put a 1 under them. And they're all fractions. Okay? So, if I am an integer, I'm also a rational number automatically. Now, what this then also includes would be something like, I don't think green will show up nicely. This may include like a 2/3. Okay, something like that. Now, the other version of a partial number besides a fraction could also be a decimal. Decimals can also be rational numbers as well. Only certain decimals, though, can be written as fractions. So how can we recognize that? So first thing with a decimal, rational numbers are also decimals that terminate or repeat. Terminate means it stops, like a 0.5 or a 0.27, something like that. Repeat means it could go on forever, but it's a repetition. So 0.33333333, 0.79797979. There's a repetition within that pattern. That's where we're also going to have a rational number. Okay? Now, this next set is kind of a standalone set, and that's what we call the irrational numbers. Okay? Now, the irrational numbers, think of that prefix IR. That just means not rational. Okay? So if rational numbers can be written in the form A over B, irrational numbers are numbers that cannot be written in the form A over B. Okay? That is very, very important to notice. Again, it cannot be written as a fraction. Now, when something cannot be written as a fraction, typically it will be written as a decimal or can be written as a decimal, but it's a decimal that does not terminate and does not repeat. Okay? So you could also say these are decimals that do not terminate or repeat. Okay? So that would be like a 0.3947869 ... that goes on forever. That would be an irrational number. Also, square roots that don't come out nicely, like a square root of 7, that would be an irrational number. So, last one here are real numbers. Real numbers pretty much cover everything that we've just talked about. So real numbers, all of the above. Okay? There is something called an imaginary number that you will talk about later in 098 or intermediate algebra, but right now we're only talking about real numbers. Okay, now before we get into some examples of this, there are some abbreviations for these so we don't have to write out that whole name every single time. So let's go through those. Natural numbers, if we want to abbreviate that set, you simply make an uppercase N, and a lot of times you double up that crossbar, and that would be a way to abbreviate the natural number set. Whole numbers, uppercase W. Integers, a lot of people think I. We're going to use I for irrationals. Integers, we are going to use Z. Okay, and it comes from the German word for number. That's where that Z is coming from. Rational numbers, we are going to use a Q, and again, sometimes we put that like a vertical bar in there just to kind of set it aside so it's something special as a set of numbers. The Q comes from the idea of these fractions. Remember, fractions are based in division, so Q stands for quotient. And then finally, real numbers is an R with a double vertical bar. Okay, those are just some short abbreviations just so we can navigate this a little quicker. Okay. Next, let's talk about some applications of this. What kinds of questions they typically ask in this section, and what I want you to be able to do is to classify certain numbers. Okay. When I say classifies, what set do these numbers fall in? So let's start with something simple. Let's say 3. Okay. Now, I like this list as it's written because it builds upon itself. Whenever you're trying to classify, start from the top and work your way down. Now, these 4 are going to build upon one another. Once you fall into one of these categories, you're going to fall into every category below it. So if I'm natural, I will also be whole, integer, rational. If you don't fit into any of these, you would fall into an irrational. Okay? And then real, that's going to be every single number that I give you right now. Again, there are numbers that are not real. I'm not going to show you those right now. So if I look at this, 3 is a naturally occurring counting number. So 3 is a natural number. If it's natural, it's also whole, integer, rational, real. That's it. Okay? It falls into natural. A whole number just adds on 0, so it would also fall there. It's an integer. It can be written as a fraction, so it's rational. And again, everything is real. Next, how about this? Negative 1/5. Now, I wouldn't count with a negative 1/5. It's not 0, so it's not whole. Now, integer, a lot of people want to say that this is an integer because it's negative. If all we knew were integers, the negative would make sense, but we would look and say, what's this 1 line 5? What is that? That doesn't really get defined with meaning until we get into rationals. Okay? So the first thing we hit here is rational. And then real. Again, it is not an integer because we don't have, I like to call these solid numbers. Okay? Not whole because we have a category called whole numbers. But these are solid numbers. Okay? This is not a solid number, so it would have to go into the rationals. Next, how about 9/3? Now, careful with something like this because 9/3 is a fraction. However, that can be simplified to a 3. And now we're back to this. If you can simplify or work something out, do so before you categorize. So this 3 is going to be natural, whole, integer, rational, and real. Just like it was up here. Next one. Square root of 7. Okay. Now, square root of 7, if you pick up your calculator on that, you would get something in between a 2 and a 3. It would be like a 2 point something. Okay. But it would be a point something that does not repeat and does not end. So something like this would be an irrational and real. Now, on the other hand, let's say we have square root of 4. Okay, don't think that all square roots are going to be irrational because square root of 4, that's just a nice 2. That then gets categorized as natural, whole, integer, rational, and real. Okay? And then one more. Let's say pi. Now, pi is a little tricky because pi, by definition, is the ratio of a circle's circumference to its diameter. Okay? Now, if it's a ratio, those of you who remember ratios from the past, you're talking fractions. Okay? However, if you work that fraction out, it's a decimal that does not repeat and does not terminate. So pi sometimes can be categorized as irrational and rational at the same time. For the sake of simplicity, In this class, we are going to agree that pi is irrational and real. Okay? So again, there are times where you can kind of argue both sides of that, but we're going to say it's irrational, period, end of story. Okay? If you have any questions on anything that I'm saying here, or if you have questions on an assignment that's in my math lab, please feel free to reach out, and I will clear up any confusion you have. Okay, one other type of problem that I want to talk about happens where they give you a set. Let's see. That. Now those are randomly generated numbers. There's nothing special about them. They're just, here's a bunch of numbers. I want you to tell me which of those are natural, whole, integer, rational, irrational, or real. Okay? Now, from this, which are natural? Which numbers would I count with? I would count with a 7. I'm not going to count with any of these other numbers. Now, whole numbers, here's the interesting thing. If I list them out in this order, once 7 is included in natural, remember, 7 is whole, 7's an integer, 7's rational. That's going to build upon itself. Now, whole numbers, what else was included with whole numbers? That's where you get that 0, and there is a 0 in the set. Okay, if there's no 0 there, then I wouldn't be putting 0. Now again, once that hits whole numbers, it's also an integer, it's also rational. Okay? Now, as I go down to integers, which of these is an integer? I already know 7 and 0 are integers, but also -5. That's an integer as well. Okay? Again, I can throw that here. Now, next, rational numbers. We already said that's rational, that's rational, that's rational, and this is rational as well. See how this builds upon itself. Okay? Now, irrational numbers, these are all rational, so they can't be rational and irrational at the same time. We want to separate those. This right here is a decimal. Notice this tells you it goes on forever, and there's no noticeable repetition within that number. Okay? So that is an irrational number. If there's a decimal that repeats, like let's say I did this, that's a different story. That bar means it's 487, 487, 487 on forever. Okay, but without that bar, I can't assume that anything is going to repeat. Okay, you may say, well, what if it's 487, 11111? Well, then I needed to show that in the number for you to see that that repetition occurs. Okay, now in terms of real numbers again is everything that we're talking about here. So if you want to list them all or just say all, that would be fine. Okay, if it's a My Math Lab thing, I would type it out because a lot of times they won't recognize that for what you're trying to say. Okay, one last thing in this section that we're going to see it from time and time again later in this course is the idea of absolute value. Okay, now absolute value is when we take a number, like let's say 5, and we put those bars around it. Make sure those bars are taller than the number, because if you just do this, I don't want you to accidentally think that's 151. Okay, so be very clear on your notation. Okay, so there's a 5. Okay, the absolute value of 5 is simply 5. Absolute value of, let's say, a -3 now. Okay, that's a 3. Absolute value of, let's say, -1.7. That's 1.7. Absolute value of 1/3 is a 1/3. Notice what we did. We kept the number exactly the same. but we either kept a positive or changed a negative into a positive. Okay? That's the mechanics of what absolute value is. That's why we're doing it. Okay? Or what we're doing, I'm sorry, but why are we doing that? Absolute value by definition is the distance a number is from 0. Distance a number is from 0. So this is 5 units from 0. This is 3 units from 0. If you, let's say, live 5 miles from JJC's campus, you don't say, well, it's 5 miles in the morning and negative 5 miles in the evening. It's 5 miles. So that's why that negative basically just gets wiped off with absolute value, because it's considered a distance. Okay? So, again, if you have any questions on this section, please feel free to reach out. Keep working hard.